So, in this class we will see the design and construction of diaphragm wall. There are different types of berthing structures which I will explain, then we will talk about this diaphragm wall. Assume this is the shoreline and assume that this is your 10-meter contour. One of the procedure to construct the structure is you construct the structure somewhere here and provide some approaches. It is called as open type structure. Here there is no diaphragm wall. Shoreline is the line at which you will have the water level 0 and the bed level will be more than 0, or you can fill up this area. This is the open type structure. Here you will have 10-meter water depth and you can dredge this area to minus 15 meter afterwards, or minus 15 or minus 17 meters. There is no diaphragm wall, it is a open pile structure. There will be an approach and then you can construct the structure. This is a structure in which there is no diaphragm wall, there is no continuous wall which is retaining the soil. The other type of structure is, this is your shoreline. What you do is you build one structure here, what is called as a diaphragm wall. This is known as the front diaphragm wall. Basically you have to extend this on the ends. Then you have certain rows of piles. There is another type of structure in which, suppose you have the shoreline here, you construct the diaphragm wall here, but put the piles on the front. So, this is called as the rear diaphragm wall. So, we have a open type structure with approaches from the shoreline to the jetty. Then there is a front diaphragm wall with piles on the back side. So, this front diaphragm wall, the top level here will be plus 5, the edge level will be here minus 17, let us say we are designing it for minus 17. Whereas in this type of structure, this level will be minus 17 and this level will be plus 5, but this bed level here, since we are coming here let us say about 30 meter or so, and assuming 1 in 3 slope, the bed level will be minus 7. That means the difference in soil, the difference in bed level is this side plus 5, this side minus 7, that is 12 meter is the difference. Whereas here it is plus 5 here and minus 17 here, it is 22 meters. This type there is no earth pressure, is it clear? So, what here we are doing is, if you see this figure, suppose this is the structure what is shown here, the structure is shown here. Here we have more number of piles, we have about 1, 2, 3, 4, 5 piles. Here the bed level is minus 15. You have the piles here. Piles means it is a discontinuous structure, it is not retaining the soil, and when it comes to this place, here we have a rear diaphragm wall, here we have a slope of 1:3. Suppose this distance is about 32 meters, this 1:3 means the bed level will be 10 meter less here, that is about minus 5, top level is 5.8, that means it is retaining the soil only for 10.8 meters. Any doubt in this? You understood what is the diaphragm wall? Diaphragm wall is nothing but a retaining structure which retains the soil and it does not allow the soil to collapse, it is a continuous structure. Is it clear or not? Huh? What is it? See, depth means it has to go below the sea, below this bed level to sufficient depth, that we will be calculating. I will tell how to calculate that. Now, pile depth criteria is different, diaphragm wall depth criteria is different. I will tell you how to define the pile depth, how to define the diaphragm wall, both the things will be explained. This class I will explain what is the diaphragm wall depth. The other case what is shown here is it is a front diaphragm wall, here the dead level is minus 12.5, top level is plus 5, but it has to take the earth pressure from plus 5 to minus 12.5, that is about 17.5 meter it has to take, and the piles are on the back side. These are all the piles which are on the back side. This is the diaphragm wall, that is this type of structure. There is one more structure which is in between these two, which is recently done. This is the type of structure. This is something like this. In this type of structure what we are doing is we are filling this area with a slope, so that this will be used for, this is the reclaimed area, reclamation is carried out. So, this is used in second container terminal, at Chennai Port Trust. So, here you can stack the containers. So, here what you are seeing is this is the slope what I have shown by this line, this line is that slope, this is the structure, and we put some tie back system for mooring pull, and we fill this entire area by sand, then we put some rock toe embankment, this is called as a rock fill. What we are giving here in the slope is rock fill. What is shown in the board is the plan, that is when you look from the top how it will be seeing. What I am showing in the PowerPoint is the cross section, how it will be like that. So, this is done in Paradip Port. This is done in JNPT. Out of these three concepts, which will be better? What is done in Chennai Port, or what is done in Paradip Port, or what is done in JNPT, which will be better? That is what is done in Paradip Port. See, Paradip Port, the problem is, see, whenever we go for the design, there are three parts in a design. One is estimation of force, second is analysis, third is the design. These are the three components for any design. First is the force estimation, second is analysis, third one is the design. If we talk about the forces, for which structure the force will be less? First structure or second structure or third structure? first will be less because there is no earth pressure. Earth pressure is taken by rock to embankment. Which will be more? First one, second one, or third one? Not third, second only. Second, the top level is plus 5, dredge level is minus 17, that means 22 meters it has to retain the soil, that means the force will be more. So, if you assume all the cases the bed level is minus 17, top level is plus 5, the first case there is no earth pressure it has to retain, there is no differential water pressure it has to retain. Second case it has to retain from plus 5 to the dredge level minus 17, that is 22 meters. The third case it is from plus 5 to minus 7, that is only 12 meters, right. Based on that is why the front diaphragm wall or rear diaphragm wall, these are the two cases. There are certain cases where we go for no piles at all. This is another case, this is the main diaphragm wall in the front, this is the rear diaphragm wall, then you connect it by a tie back system, the whole area is filled up and the soil is supposed to take all the load. This is another type of system that is practiced. So, we have a front diaphragm wall, we have a rear diaphragm wall which is a dead man wall. So, we will be discussing about the main diaphragm wall. Main diaphragm wall means it is retaining the soil. So, this is the terminology which we will be discussing. So, whether we have a front diaphragm wall, main diaphragm wall or rear main diaphragm wall or no diaphragm wall, these are the three cases which we will be discussing. And the fourth case what we will be discussing is we will have a front main diaphragm wall and the rear dead man diaphragm wall. Dead man diaphragm wall is a structure which does not allow the main diaphragm wall to fall back, that is why it is created. It is an anchor wall. So, the construction is either concrete or steel. Suppose let us say it is a concrete structure, it is continuously built. While building we will have the soil level at both the sides same. Then what we will be doing is we will be removing the soil to certain level. Suppose you remove this much portion of soil, that is this much portion of soil is removed. What happened? This diaphragm wall acts like a cantilever diaphragm wall, right. This is called as a cantilever diaphragm wall. That means we will do dredging and remove the soil on the seaside, so that the ships will come and rest. This is for fishing harbor it is done. So, this is called as a cantilever diaphragm wall, there is no tie back. Suppose you want to dredge deeper, suppose you are going right up to this, more depth is there, that means you are removing this much soil also. So, what happens, this embedment depth is not sufficient, so it will not take the load. Then what you do is you put a tie rod, then put a dead man wall. Suppose generally this level is about plus 3 or plus 4 or plus 5, I will assume it as plus 5, generally used as minus 2 for fishing harbors. For up to about 7 meter of unsupported length, you can use this cantilever type diaphragm wall. Cantilever type means there is only the diaphragm wall with sufficient embedment depth. This embedment depth is approximately equal to 7 meter for medium type soil. If it is a very good soil, you can take 75% of this, but you have to do the calculation. I will tell how to do the calculation later. If you go more than 7 meter, see for 7 meter embedment depth, this thickness of the wall, that is the thickness of the wall, this is for cantilever type, is this length is 7, L by 7, that is approximately 1 meter. So, if you see the span by deflection ratio in IS 456 for a cantilever, they say the depth of the cantilever should be span by 7. So, if there is a beam here, there must be a beam here, but they have they have put the false ceiling. There are 3 cases given. One is cantilever, another is simply supported, third next is fixed. Cantilever is L by 7, fixed is L by 20, I think this is L by 27 also, right. By 29, I do not remember, it is given in IS 456. See, serviceability criteria, we have to check for deflection, but if you provide the depth greater than L by 7, if it is a cantilever, you do not have to check for deflection. If you provide more than L by 20, you do not have to check for simply supported, more than L by 27 or 29, you do not have to check for fixed. This is what is given here. But when you go for this case, this will be in between this L by 20 to L by 29. Suppose we take L by 20 and this distance we take it as minus 15. So, this is 5 meter, this is 15 meter. So, this is 20 by 20, this also is 1 meter. So, the same 1 meter thickness you can provide for the diaphragm wall even if the dredge level is minus 15, provided you substitute an anchor, right. Is it clear? If you do not do it for cantilever, this minus 15 plus 5, 20 meter, 20 by 7 is how much? 20 by 7, close to 3 meter. If you want to provide this as a cantilever, you have to provide 3 meter thickness, it is very difficult to do, that is why you go for a tie back system, right. And when you provide a tie back system, this soil is collapsing, this soil will go down like this. Suppose this diaphragm wall is not there, assume that the diaphragm wall is not there and you are dredging up to minus 15, what will happen to the soil? Soil will not remain vertical, it will collapse. This is angle of repose, it will collapse. So, up to this area, even if you provide a pile here, it will not provide any resistance. Similarly, here also there is a distance called passive resistance. So, this distance should be sufficiently more, it is about typically about 30 meters. You have to calculate where to locate the deadman diaphragm wall. It cannot be very close here. If you put the deadman diaphragm wall here, what happens? It will be in the active zone, it will fail. Anchor wall should be provided far away from the main wall. I am explaining this here because one of the structure very recently built, they have not put the diaphragm wall, deadman wall properly, the whole structure has collapsed, 45 crores lost. One of the structure very recently, some 3 years back. The other important parameters to be studied are soil properties. So, I said you have to do force estimation, analysis and then design. The force estimation, you should know what is the soil properties. Unless you know the soil properties properly, you cannot estimate the force correctly. Then we have to go for analysis. We are doing the analysis using one software called StatPro. Then design, there are 2 types of design, limit state of collapse and limit state of serviceability. Then diaphragm wall, it can be a rectangular wall or a T wall, that also we will see. Then after this force estimation, analysis and design, the most important requirement is reinforcement detailing. The detailing of reinforcement is very important. 99% of the structures which are failing, which have failed, is mainly because of improper reinforcement detailing. Even if you have done the correct estimation of force, analysis and design, if you do not properly detail the reinforcement and execute in the construction, then the collapse will take place. So, this is important, that is the reinforcement detailing as well as construction is important. So, we will talk about the 4 case studies. The first study is the front main diaphragm wall tied back by cross beams to vertical piles. This is for a smaller size vessel. The length of the berth is 250 meter, width of the berth is 25.3 meters. This 250 meter is divided into 5 blocks, each of 50 meter with a expansion gap. The berth is having a 1.1 meter thick diaphragm wall in the front side. The rear side is supported by 1 meter dia pile and 1.3 meter diameter pile, and the cross section is shown here. This is your front diaphragm wall, which is 1.1 meter thick. This pile is 1 meter thick diameter. These two piles are 1.3 meter. The last pile is 1.3 meters. This angle of repose, the soil here will not give any resistance to these piles. That is why we have gone for a smaller diameter pile, because we do not expect this to take more load, because in the active zone of the front diaphragm wall. The embedment depth is given about 11.5 meters below the bed level, that is about 23 meters, and these two front rows of piles are given 22.5 meter founding level. The last 2 rows are given minus 20 meter founding level. This diaphragm wall is continuous, but it is made of about 4 meter panels, and these piles are spaced at 4 meters center to center. Then we have a main beam connecting all this structure. So, when the diaphragm wall is trying to deflect, they transfer the load, they are tied back to these piles, and these piles will not allow the diaphragm wall to fall down. That means, whatever force that is acting on the diaphragm wall, some portion of it will go below the seabed, some portion will go to the piles back. Normally 50% of the total force acting on the diaphragm wall will go to the diaphragm wall below the seabed, and the other 50% will go to the piles behind. This 50% of the force acting on the diaphragm wall will not go equally to all the piles. The piles of bigger diameter will take more force, the piles in the active zone will take less force. Then we have the next system that is done in JNPT. This is for a diaphragm wall, rear main diaphragm wall is shown here. This is the rear main diaphragm wall. This thickness is small, 0.85 meter only. We have 1, 2, 3, 4, 5 rows of piles. Typically 5 rows of piles are used. This is the sea side, this is the land side, and the total length of this diaphragm wall is given here. I do not think it is given here. It is for a typical block of 60 meter. Like that we have multiple blocks. I think totally it is for about 600 meter or so total length, and there is a spacing in this direction. We have given this in row numbers 1, 2, 3, 4, 5, 6 like that. This is numbers are given here. This side it is given A, B, C, D, E, and this is your F row, and these piles are of different diameters. Diameters are given here, 1200 mm thick, 1200 mm diameter pile, and the diaphragm wall thickness is 850 mm. Spacing of the pile in the longitudinal direction is 6.4, that is, this is the longitudinal direction. Here the spacing is about 6.4 meters center to center, and the transverse direction first row is 2.7 meter, then 7 meter, then 6 meter, then 4.5 meter. If you see here, distance from here to here is I think it is 3.3, it is not 2.7, it is given as 3.3 meter. From here to here is 7, from here to here is 7, then 6, then 4.5, then 4.5. What is the criteria for fixing this spacing? The spacing between the piles, how close it can be? We are putting 2 piles, how close you can put 2 piles? Suppose the diameter of pile is 1.2 meter. 3 the code specifies that the minimum spacing between the pile is about 3 times the diameter of the pile. 1.2 meter means you should not put closer than 3.6 meter. If you get, then you have to do the group effect, then the piles will not have the same capacity if it is at a closer spacing. The spacing is generally given about 7 meter, because for construction purpose when you have to put the precast units, the weight there is a limitation, maximum spacing is between 7 and 9 meters only. The weight is more, the lifting capacity is more, you have to, here water is there in this area, so you have to lift these beams and place it, that is why they put about 7 meter as a spacing. And from the fascia beam to this central line we provide 3.3 meters, mainly because we have to put some bollards, there will be some cranes which will be going, you have to put some service trench, for all these reasons this gap should be about 3.3 meters. So you can play with the layout, changing the spacing. I have given 6.4, you can make it 7, 7.5, 8, 9 and see what is the diameter required. So if the spacing is more, diameter will be increased. And we have shown 2 beams here, this is for the front crane beam, this is for the rear crane beam over which the crane will move. This is the rear diaphragm wall. The deck system consists of RCC slab 190 millimeter thick cast in situ and 310 millimeter thick precast, that is the total thickness of the slab is 500 millimeters. Normally in residential buildings you will see only 200 or 250 mm thickness, whereas for harbour structure we put 500 mm thick, because the load on this structure is 50 kilonewton per meter square, whereas for building it is only 5 kilonewton per meter square. On top of it we will have some mobile harbour cranes which will give a load of 2000 kilonewton per meter square, very high loads, patch loads. Then we have the beam sizes 1400 millimeter by 3150 millimeter, and different sizes are given, fender beam size is given, edge beam size is given. So these are all the requirement for the design. What is the slab thickness here, what is the beam size here, what is the beam size here, all these things govern the design. This shows the cross section, front pile, the rear piles and the main diaphragm wall which is put on the rear side, and plus 5.8 is the level here, this is the chart datum, the embedment depths are given. Since the rear diaphragm wall, the main diaphragm wall is provided in the rear side, the founding level can be lesser, it is minus 18 only, whereas here it is minus 19.5 for the piles. It depends on the soil profile, here we have rocks available, that is why though the dredge level is minus 15, we are stopping at minus 19.5. So if you provide a rear diaphragm wall, the founding level can be lesser compared to the piles, whereas if you see the other case, the front diaphragm wall is minus 23, whereas the rear piles are minus 20. This has to be done by design only. After doing the analysis we have to do 2 design, one is structural design and another is foundation design, based on which we have to do. So whenever there is a berthing force which is a main force for which it is designed, it is hitting the structure here, all the load will go behind the rear diaphragm wall to the soil. This point is clear, no? When you are hitting the structure with berthing force, the whole load will go behind the soil, soil will take the load, but only when the vessel is pulling the bollard, that time the diaphragm wall has to take the load. But seismic force in this direction the soil will take, but seismic force in this direction the diaphragm wall has to take. This is the third case study in which these 3 numbers are different from what is shown in the board, this is a different case studies. So here what we are doing is we have 820 meter long berth, we are dividing into 13 modules, we are providing expansion joint of 40 mm thick and every 60 meter, the width of the berth is 37 meter. We use different types of piles, here we use board cast in situ pile, the pile spacing is 7.5 meter in the longitudinal direction and 7.62 meter in the transverse direction, we have 2 crane beams. What for we are providing expansion joints? What is the reason for providing expansion joint? What happens if there is thermal expansion and if you do not provide expansion joint? Cracks will come, but you can design it, suppose you design it properly, you can increase the spacing. In Tuticorin we have provided 300 meter without expansion joint, but you have to design for it. Design means when you do the analysis you have to design it for temperature difference, find out what is the forces in the slab, beam and piles, then you can design for it. But normal building the span joints are provided between 45 meter and 60 meter residential building, whereas for berthing structures Tuticorin we have built 300 meters, JNPT we have built 150 meters, no expansion joint in between that 150 meters. So, we are providing one cut off wall, then we are providing one dead man wall, and then we are connecting these two by a tie rod. The anchoring system consists of 120 millimeter diameter tie rod and the spacing is 2.5 meter. What we are seeing is this is the cut off wall what we are providing here, and this is the dead man wall. This is connected by a tie rod. Generally the tie rods are not at the top level, it is somewhere at the lower level, typically it is at 0 level or slightly above. This dead man, see whenever there is a bollard pull, so we do not want to transfer it directly to this diaphragm wall here because there is no diaphragm wall. So, what we do is we want to transfer it to a dead man wall which is kept far away, maybe it is more than about 15 meter or so, so that the dead man wall will take the tie force. That means we have only the piles which are provided. The transfer spacing is given 7.62 meters center to center, the longitudinal spacing in the other direction is 7.5, whereas the tie rod are provided at every 2.5 meters center to center. The elevation here is plus 3 meter tie rod, the top level is plus 4.8. Typically this plus 3 meter is the center line of dead man wall. Dead man wall will be from plus 4.8 to about minus 1 meter. So, we go to the center and provide this anchor wall. This figure is clear to you. We build the structure in open sea where minimum dredging is required, then from this portion to this breakwater where it exists in Chennai port we use sand fill, then we use some big size stones, this is a core stone, then we use a armor stone, the slope is 1 vertical to 1.8 horizontal, then we anchor this below the bed level by some material which is as big as the armor stones. This is the fender which will go down below the lowest water level. This is what is called as a toe protection, what is given here. This is a toe protection given, and it is also given to reduce the propeller wash. When the ship is coming, the propeller is moving, the propeller will create some disturbance, due to the soil will cover. So, this will act like a toe protection, plus it will also act like a cover protection against propeller movement, current generated by the propeller.
So, how much is the thickness of each of the dead man wall?
No, here dead man wall is maybe around 1000 millimeter thick. You are asking here or at other places? At that end. This layout about 1000 millimeter I think, or 850 I do not know, it is 800 millimeter thick and it is 3 meter depth and its distance is 14.5 meter, that is this is 3 meter width, 3 meter depth, this thickness is 800 millimeter, the distance from here to here is 14.5 meters. That means the active pressure on the cut off wall and the passive pressure from the dead man wall should not meet, there should be a gap. This structure is found to be about 30% economical compared to any other structure which we have built earlier. Now, we will complete this lecture class with this case study. This is one of the oldest method which is used. Instead of using concrete, they used a steel sheet pile wall. One of the mistake they have done is they used a front main sheet pile wall tied back to dead man sheet pile wall. They used it in soft clay with lot of silt draining into this area. The soft clay, it is recommended not to use this sheet pile wall, steel sheet pile walls, because soft clay if you go for the earth pressure calculation, earth pressure will be very high. If it is a medium dense sand, you can go for steel sheet pile wall. They have gone for a soft silt. Other problem, the design was carried out based on soil investigation, not in the final alignment of the berth. Suppose you want to construct a berth in ICSR building, you cannot take the soil investigation at ocean engineering department. Originally they proposed near ocean engineering department, they did the soil investigation. Based on that soil investigation, they have constructed a berth at ICSR building. The soil is different. Suppose you go to our department of ocean engineering or civil engineering department, you get a rock at a depth of about 1 or 2 meters. You go to Sharavati hostel, you get very soft clay. Have any of you gone to the academic complex? Otherwise you ask Gandhi to take you there. Yeah, they are doing the foundation, they are doing a isolated footing where they are excavating and they get the rock. Whereas when you go to Sharavati, which is very close to the lake, where we have very soft clay deposits for a very deep depth, maybe 3 meter, 3.5 meter, you will not get the rock. So, if a type of foundation required at 2 different places are different. Academic at the administrative building in our IIT campus and Sharavati hostel, the distance may not be more than 100 meters. Administrative building soil is good, Sharavati hostel it is not good. In what we see is about 40 to 60 meter spacing, you have to do the soil investigation. It is likely that within 40 to 60 meter the soil may vary, in some places even 20 meters it may vary. So, then considering the heavy fluid nature of the clay, the choice of sheet pile is totally unwarranted, but they have gone for this. So, they have provided this main wall here, they have put the dead man wall here, they have located the dead man wall, whereas this active zone itself they have located. The distance should be more than 30-35 meters, they have located within about 20 meters. That means the full dead man sheet pile wall will not get any passive resistance, only some portion below this active wedge only will be resisting. After failure of the structure, the soil investigation has indicated lesser cohesion compared to the design cohesion assumed based on one borehole investigation. This berth is 300 meters. When you go for 300 meters, you need at least 6 boreholes. What they have done is with one borehole, that also not at the location of the berth. The dead man sheet pile was not located beyond the passive rupture surface and was terminated in soft clay zone, which was highly undesirable. See, when you locate this dead man wall, it is not the depth of embedment of the dead man wall, it is also where the tip is, where the bottom level is. The bottom level should be in either rock or in sand. What they have done is, in this particular place which is at Visakhapatnam, we have up to this level we have only clay, below that you have rock. If you have rock, what they have to do is they have to bore by another equipment, then they lower the sheet pile wall. Since they did not do that, both the main diaphragm wall as well as the dead man sheet pile wall is not anchored into the rock, it is stopping only at the clay. So, that is not correct. Then the groundwater level considered in the design of dead man wall is the same as the main wall, whereas this particular code recommends higher water table for dead man wall. So, what they say is, that is why you have to read the code. You are assuming some water level here, because this is very close to the sea, the water level will go up and down, not as fast as the tide, but it is rapid, whereas at this place the water level will not go up and down very fast, because this is a clay layer which is impermeable. Suppose the water level is here, the tide level goes down here, the water level will not come down very fast. Is it clear? We will be discussing this one of the next class, how to calculate the differential water pressure. Differential water pressure means we assume lowest water level here and some groundwater level here. If it is impermeable, the groundwater level should be very close to the mean sea level, but at this place it should be as close as to the top level, but they have not done this. when you do the analysis, if this is kept at mean sea level, which is about +2 or so, this should be kept at +5, which they have not done. The post failure investigation has indicated 1 meter higher water table. So, they measured the water table after the failure, they find the water table at this location is 1 meter higher than at this location. The load combination of surcharge load behind the dead man wall and no surcharge in front of dead man wall has also not been considered in the design. That is, when you calculate the earth pressure, what you have to do is you have to assume some surcharge load. What is given in 9527 code is you assume the surcharge here and assume no surcharge here. Surcharge means we are talking about 50 kilonewton per meter square, that is 5 tons per meter. Suppose you stack the cargo here about 50 kilonewton per meter square, that means about 5 meter of soil approximately with submerged density of, that is another 5 meter soil here, that is what you are assuming to calculate the earth pressure. What is given in the code is you assume that the cargo is not stacked in this area, it is stacked only on the back side, that is what to be assumed in the analysis. So, there are 2 cases we are considering. One is the water level should be assumed higher here, another is you assume the surcharge load only here, not here. These 2 cases comes both in the force estimation as well as in the analysis. So, if you do not consider these 2 cases, then the structure will fail. So, this is what has happened. So, I will repeat again, the soil investigation adequate number is not done, the exact location it is not done. Dead man sheet pile wall is very close to the main wall, it should be further away. The founding level should not be in clay. Third is groundwater level at the dead man wall should be higher than at the main wall. The fourth is it is 1 meter was indicated as the difference. The surcharge load should be assumed behind the dead man wall, not in front of the dead man wall as one of the load combination. Then about the expansion gap, it can vary from 60 meter to 300 meter, depends on the type of structure, depends on the type of soil. If the soil is uniform, you can go for 300 meters. If the soil profile varies, it happens in Port Blair, every 30 meter also we provide expansion joint. We also should check the deflection during earthquake. Then expansion calculated considering limit state of serviceability load combination, you have to calculate and provide that expansion. Do not provide 20 mm 40 mm as the expansion gap, you have to calculate what is the deflection due to temperature difference, and accordingly you have to provide the expansion gap. Especially during earthquake, the expansion gap requirement will be more in seismic zone 4, 5 and all. The design crane track is continuous, that should be designed suitably at expansion joints. So, from next class onwards we will discuss about this soil properties and continue the discussion.